Hello everyone. So we are going to discuss a very important aspect of geomorphology, that is plate tectonic theory. Okay. So what does this plate tectonic theory explains? It explains that how the contemporary world map was formed, how the map was formed and what was the process. So these are some of the theories. Okay. Continental drift theory, he gave the concept of polar wandering, sea flow spreading theory, convection current theory, and plate tectonic theory. These four theories we are going to deal, and they are very, if you analyze the PYQs, okay, as we know from 2014-15, the questions of geography were much more oriented towards mapping, but the rejuvenation of physical geography like geomorphology, climatology and oceanography was seen in 2022 and late 2023 papers, and especially in 2024 prelims there were a lot of questions from this physical geography part. So let's understand this concept in a very crisp and concise and comprehensive manner. The first theory that we are going to understand is continental drift theory. Okay, who gave this theory? It was given by a German geographer Alfred Wegener. Okay, what did he say? He said in ancient period, in ancient period there was only one supercontinent. Okay, it's technically pre-carboniferous era, millions of years ago. There was only one single supercontinent, one single landmass. Its name was Pangaea, and there was only one ocean body. Its name was Panthalassa. Pangaea and Panthalassa. Now, what happened? There he assumed certain forces. What were the certain forces? Okay, he did certain assumptions. He said certain multiple forces were acting on this Pangaea and Panthalassa. Okay, this is Pangaea, the supercontinent, and this is Panthalassa. What's happening here? As you can see, he did certain assumptions. Okay, Pangaea, Panthalassa, that is C. Okay, he said the Pangaea, which is a continental landmass, it is made up of Sial. What is Sial? Sial stands for silicon and aluminium. And the water body Panthalassa, it is made up of Sima. Okay, its base is made up of Sima, that is silicon and magnesium. Okay, he always said that the oceanic plate, the ocean bottom is much more denser. Okay, so the scenario is somewhat like this, that the Pangea is floating over the Panthalassa. Okay, the Sial, the continent, is floating over the ocean. This was the first assumption that he made. Pangea, Panthalassa, the continents are floating over the ocean. Okay, fair enough. Now, second, Sial floats over Sima. He said there are certain universal forces in the nature. What are those universal forces? The first force is the tidal force. Okay, I'll explain it here. Okay, the first force is the tidal force. What is tidal force? It is gravitational pull of sun and moon. Okay, the gravitational pull of sun and moon are said to be tidal force. Okay, the phenomena of tides, in Hindi we call it as jwar bhata, rise and fall of the sea level, occurs because of it. Okay, the second force is polar fleeing force. Okay, what is polar fleeing force? Polar fleeing force is just because of the rotation of the earth. Okay, it's because of the rotation of the earth. It somewhat obeys Newton's third law. Okay, in the direction where the earth rotates. Okay, so as Newton's third law, which has equal and opposite reaction, the continent tends to rotate or move in the opposite direction of rotation of the earth. Okay, the third force, the third force it is a type of a endogenic force originating from the interior of the earth. Although this force was not very well explained by Alfred Wegener, this force in detail explained by thermal convection current theory that we are going to study just in 10 or 15 minutes. Okay. So what was the third force that he considered? He considered gravitational force, and the fourth force was the frictional force. What he said, that since Pangea is floating over the Panthalassa, what's happening here? Okay, there is a friction between the two. There is a friction between the two. Okay. So these are the prominent forces, and the fifth force that he considered was buoyant force. Now, what is buoyant force? We have studied in ninth class NCERT the Archimedes principle. What is the Archimedes principle? In Archimedes principle, it says, what does it says? That why does an object floats over a water body? Because there is always, suppose this is a water body and something is floating over it. Why it is floating? Because there is always an upthrust force, upward force that is exerted by the liquid on this water body. Okay, so this is the force that makes the that makes any of the bodies float. Okay. Further, we are not going into the details of Archimedes principle. It says that the volume of weight displaced is equal to the submersible part of the solid which is floating over the ocean. But one thing that you need to remember, it is an opposite force to gravitational force. Gravitational force is acting downward, and it is an upthrust force that makes the body floats. Okay. Now, with the application of these five forces, okay, he said the Pangea, Pangea is going to break into two major parts. What are the two major parts? One continent, that is Laurasia. It is also said to be Angara land. Angara land constitutes the continent of North America as well as the Eurasia. Okay. And the southern part, it is said to be Gondwana land. What's happening here? The Pangea is getting split into two parts. Okay. The Gondwana land constitutes the continent of South America, Africa, India, Antarctica, and Australia. I hope it's clear. Okay. And in between them, between these two big land masses, the land masses are like this. This is Angara land and this is Laurasia. Okay. Sorry, this is Gondwana. And the water body between these two massive continents is said to be Tethys Sea. The event is known as opening of Tethys Sea. Opening of Tethys Sea. Okay, this was the major event. Now, what's happening here? There were further these forces were acting, and again there was again simultaneous closing of the Tethys Sea. And after closing of the Tethys Sea, when Gondwana and Laurasia both collided with each other, the big land masses broke into certain pieces. As you can see in Gondwana, the Gondwana land broke into South America, Africa, India, Antarctica, Australia. Okay. Similarly, Laurasia broke into North America and Eurasia. Eurasia stands for Europe and Asia. And now the action of polar flinging force came. Since the earth rotates from west to eastern direction, the continents start moving. They started drifting westward, following the Newton's third law that every action has equal and opposite reaction. Okay, so they started moving, they started drifting westward. Now what happened? And eventually North America came this side, Eurasia stayed there, South America, Africa, and the contemporary world map, the world map that we are seeing now, was established. It was because of the westward movement. This was all about the Alfred Wegener's theory. But don't you find something fishy in this theory? Something might be fishy in this theory. What's that, the fishy part? What was the criticism? The theory cannot be so simple. Okay, just the continents are broken into pieces. The land masses are broken into pieces into several continents, and they start drifting westward. And the map is formed. It is not that simple as it appears to be. Why? Okay, first let's talk about some of the criticisms. Okay, first of all, the major criticism. Do you think? Just let me come here. I just want to add a slide. Okay. Here it is. Okay. What do you think the first criticism of this theory, that the forces, what are the forces? These forces that we talked about. These forces, tidal force, polar flinging force, gravitational force, frictional force. Okay, tidal forces is only that strong that it can only lift the water up to 5 to 6 meters of height. Gravitational force is a very weak force. It is one of the most feeble force. So are they enough to break such huge land masses into certain pieces? What Wagner said that by the application of these forces, okay, the land masses collided and they were disintegrated into very small pieces. So do you think are they strong enough? This makes the first criticism, that no, these forces are not at all strong enough. These forces are not at all strong enough to break them into multiple pieces. The next criticism, why the continents were moving only westward direction. Newton's third law, polar flinging, is not the accurate explanation. Okay, as we see, India, India was earlier a part of Gondwana land, but how now it has become part of Laurasia or Angara land? You can see here. Okay, as you can see India is here, so it should not be in the, it should be in the southern hemisphere. How it came to this part? Alfred Wegener did not have any answer. Okay, so what he said, that the that these continents are drifting westward, but India, it has drifted to the north eastern direction. What was the mechanism? He could not explain. Now, next thing, how the mountains, plateaus, plains, the intercontinental lakes, how they were formed. Wegener did not had any answer to such questions. Okay, let's see some of the more criticisms. What about the Tethys Sea, where it is now? It was not explained by Alfred Wegener. Okay, Wegener said that drift began only in Mesozoic era. Why not in the pre-Carboniferous era, pre-Cambrian era? It is actually geological time scale, not at all relevant from your GS point of view. So the time scale was also not properly explained by Wegener. Okay, especially that I talked about the forces like buoyancy, tidal, they are not at all enough to move these continents. Okay, but is it so? No. His theory was not totally rejected because it has certain positives as well. Now, what are the positives? Let's see what are the positives. Or we can see what are the evidences of this theory. Okay. The first evidence, okay, the zigzag fit of the continents. Okay. If you should see the Gondwana land, if you see the Gondwana land, okay, if you just fix the continents, the bulge of South America with the depression of Africa, this is Gulf of Guiana, and this is the regions of Brazil. They fit each other like puzzles. Exactly, the continents were not fitting like puzzles because of erosional features of air, water, wind, but approximately 1,000 meters beneath the continent, they were easily getting fixed. So it shows no, Gondwana land must have existed. Similarly, the evidences were for Antarctica, India. See, they all are getting fixed like a puzzle. Similarly, Greenland, it fixes with Canada. Okay, the west coast of India and Madagascar seems to be and Africa seem to have been joined. These are the evidences. Now, paleoclimatic evidence. Okay, I'll explain some of the evidences. This was zigzag that I was talking about. Some other evidences, prominent evidences. Okay, I'll just add a slide here. Okay, the first is paleoclimatic evidence. What was seen here? It was seen that especially in the regions of northern Europe and northern Canada, okay, in the regions of northern Europe and northern Canada, this part, coal deposits were found. And we know how the coal are made. Coal are made when the evergreen forests are being submerged, and with intense heat and pressure they are converted into the fossil fuels. So it shows, what does it shows? That once Eurasia and North America might have been near the equator where they are tropical evergreen forest. It shows the existence of Pangea and Panthalassa. It is a support. Okay, it is paleoclimatic evidence. Paleoclimatic evidence, that means it shows the traces. For example, the coast of Orissa, it has tillite deposit. Tillite deposits are the deposits that are found under the glacial landforms. They are packed under the ice. So how can the Orissa region have this type of deposit? It shows that once India was a part of Gondwana land. Okay, it is paleoclimatic evidence. That means the climate of one area influence the climate, the evidence of climate of one area is found in other regions as well. And why it is so? Because of the transboundary movement, because of the movement of continents from one place to another. Okay, another evidence is placer deposits. What we see, the coast of Brazil, the rivers of Brazil, as well as the rivers of Ghana, the Niger River, they have some of the minerals deposits, gold deposits. How can the deposits of Africa and the deposits of South America be same? It can be same because they might have existed together in one common place. Okay, tillite deposits I have explained. Botanical evidences. What are these botanical evidences? The plant species are common, especially in North America, Europe. That shows that they might have been a part of common continent. Okay. Paleomagnetic evidence. Okay, what is paleomagnetic evidence? As we know, the geographical north and the magnetic north of Earth is not the same. The magnetic north pole is somewhere near Canada. Okay, the magnetic north keeps on changing its direction. So what happens? The rock structure of different continents, they have same magnetic polarity. How the rock structure of different continents, especially of Europe and North America, can have same magnetic polarity? It will be because once they might have existed together, and due to polar wandering, okay, due to polar wandering, the movement of Earth's magnetic field, they might have attained the same polarity of magnetic field, because they were once all together, and now they have separated. The continents have separated, but the direction of magnetic field in the rocks of these continents are still the same. It is the biggest evidence that yes, once the Panthalassa, Pangaea, Gondwana, Laurasia, they all existed. Okay. Distribution of fossils we have talked about. Okay, the fossil fuels, the paleoclimatic evidence, they are almost same. Moving forward. Just a minute here. So these are the evidences that we have talked about. Okay, we have also seen the criticism. Now the next theory, that was further a modification. That was further a modification over the plate tectonics. Was the convection current theory or thermal convection theory of Arthur Holmes. Okay. Now let's understand his theory. What did he give? He explained the mechanism of movement of the plates. Okay. Let's look at this diagram. Okay. Since you might have read about interior of Earth. How is the interior of Earth? There is a block of 0 to 100 kilometers. We call it as lithosphere. Lithosphere block. Okay. Below it we have asthenosphere. Okay, and here we have mantle. Beneath it we have mantle. So what's happening here? In the lower boundary of the mantle, there is some of the radioactive elements. What are these radioactive elements? Alpha, beta, gamma elements. Alpha, beta, and gamma radiations. And there is always residual heat. What is this residual heat? The heat that is being trapped beneath the rock of the mantle. Rock के बीच में जो heat trap रहती है. Okay. Now what's happening here? Because see, we all know in mantle we have magma. In mantle we have magma. Once the magma, it intensifies the radioactive elements, there is always emissions like alpha, beta, gamma emissions. So these alpha, beta, gamma emissions, they constitute what we call as hotspot. And since this part of the mantle gets heated up very vibrantly, okay, very vibrantly, it pushes the magma towards the surface. A strong magma current moves towards the surface. We call it as convection current. Convection current. It's just the rise of the magma, and what they are doing, they're striking the lithosphere block. Lithosphere block is a part of earth crust. It is made up of solid material, solid rock material. Okay, and what happens since the current is going up from this hotspot is because of residual heat and radioactive elements. Okay, it strikes the earth's crust or the lithosphere and breaks the crust into two parts. Since it provides, the hotspot provides a lot of energy, therefore since lithosphere, it is made up of soil rock structure, they act as bad conductor of heat. Therefore only 10 to 20% of magma comes out of this part. Magma comes out of this part in the form of volcano, but rest 80% of magma, the convection current, diverges beneath the lithosphere. They diverges beneath the lithosphere, and this divergence is said to be divergent current. Okay, now since they are moving in the horizontal direction, they are getting detached from their source of energy, that is hotspot. It is hotspot is at the lower part of mantle. Okay, boundary of lower and upper mantle, I would say. Upper and lower boundary. Now what's happening here? Okay, it is be getting diverged once apart. What will happen when they move aside? They will also drift the lithosphere block along with them. Like let's say this is the block A, this is the block B. Okay, when they are moving away, when these currents are moving away, they are also, because of the frictional force, they are also pulling the lithospheric block in the either direction. It's moving like this. Like see, this is convection current, the convection current is moving, my hand is the lithospheric block, which is the continent, and the lithosphere block is also moving with them. It's somewhat like this. Okay, and it is getting diverged, and eventually when the energy is lost, they come and merge back to the hotspot, making it a cell known as convective cell. And in this way, these two blocks are getting diverged. What are these blocks? These blocks are simply the oceanic bed, the oceans, or they are the continents. So he, with this theory, he explained the mechanism of movement of the continents. I hope it's clear. He explained the mechanism, like you can see here also. Okay, the lower mantle, this part is the hotspot, the convection currents are rising. In astronosphere, it is also said to be the low velocity zone because viscosity is very, very high here. Okay, the velocity reduces. Some of the magma, or I would say lava, is coming out of here. Some of the lava is coming out. It is forming ridge, mid-oceanic ridge, a chain of volcanoes, a chain of volcanoes. but majority of the currents are getting diverged. They are also, here it is written slab pull, they're also taking away the continent lithospheric slab along with them. In this way, the continents are moving in the direction of divergence of the currents. I hope it's clear. Okay. So this is the mechanism. This is the mechanism. They again diverge and come back. Okay. This whole cell is said to be convection current. So what did convection current theory said? It is also said thermal convection current theory. It explained the mechanism of movement of the plates. I hope it's clear. Now the next theory. Next theory that we are going to read is seafloor spreading theory. It was given by Harry Hess. It is exactly the same theory, the same mechanism that I explained in the convection current theory. Ditto the same mechanism. But what is the difference here? The convection current, the rise of the magma, they all are happening at the bottom of the ocean. You can see this is plate 1 and this is plate 2. They all are oceanic plates. The magma is coming, the magma is getting diverged. They are drifting the ocean bottom, the ocean plates apart. Okay, at the top we have water, at the bottom we have oceanic plates, and below it the same mechanism of convection current is happening, and the oceanic plates are getting drifted. And slowly, what's happening? Slowly, 20 to 30% part of magma is coming out. This magma is getting solidified in the form of lava and forming mid-oceanic ridges. They are forming mid-oceanic ridges like this type of seamounts. When their when their top gets flattened, they are said to be gjorts. They lead to the formation of lot of volcanic islands. The best example is mid-Atlantic ridge. With this, it is a type of silent volcano. There is also one more type of volcano, we call it as destructive plate boundaries. I hope it's clear. Okay. So what are the evidence of seafloor spreading theory? See, this is the evidence. I'll explain here. Now let's say these are two plates. This is the ocean surface, ocean bottom. The convection currents are coming in black. Okay. The mid-oceanic ridges are formed, mid-oceanic ridge, and the plates are getting diverged. The plates are getting diverged. What is the evidence that yes, this theory is true? Let's say from the mid-oceanic ridge, if we move 1 kilometer and if we move 5 kilometer, this is rock A, this is rock B. Similarly, if we move 1 kilometer and if we move 5 kilometer, okay, rock A dash and rock B dash. When we compare the rock A dash and rock B dash, they have exactly same magnetic field, same polarity and same rock structure. Similarly, from mid-oceanic ridge, when we move 5 kilometers either side, the rock structure B and B dash have exactly same magnetic field and same rock structure. What does this say? It says that yes, once they were a part of this mid-oceanic ridge, what's happening in this mid-oceanic ridge? The lava is coming out. The lava is coming out. It is getting solidified and new crust is being formed. And the older crusts are getting diverged away. The older crusts are getting diverged away. I hope things are making sense now. When they are getting diverged away, what's happening? The new crust is getting formed. It is getting spreading. So once where at this point where this new crust was being formed, when it is getting diverged in the either side, when they move equal distance, they have equal they have same nature, they have same magnetic field, Why? Because once they were part of this mid-oceanic reach, once these rocks were formed together, and because of the divergent currents, these rocks are getting moved apart. These rocks are getting moved apart, and at equal distance, the same characteristic is formed because their origination is same. It is the biggest evidence, paleomagnetic evidence of seafloor spreading theory. But similarly, what is the criticism here? Okay, the older rocks are getting drifted apart. Okay, but where are they going? We have limited amount of area on the Earth's surface. How they are getting destroyed? How the trenches are formed? It was not explained by seafloor spreading theory, and these criticisms were overcome by, okay, these criticisms were overcome by plate tectonic theory. Okay, now see, this is the distribution through the help of plate tectonic seafloor spreading. We read three types of volcanoes, earthquakes, everything, but that would be the part of next lecture, separate lecture. Only today we are confining our discussion only towards this part. Okay, the plate tectonics. The last and the most accepted theory was given by Mackenzie and Parker. It is said to be plate tectonics theory. Listen, okay. This is what we call as plate tectonic theory. Okay. Now, what assumptions did he made? The first assumption that plate tectonic theory Mackenzie Parker made, that Sial and Sima are adjoined with each other. This is Sial, that is continental plate, and this is Sima, that is oceanic plate. Continent and oceanic plate, Sial and Sima. Now, what did he say? Why Sial is thicker? Because Sial has density approximately 2.5, and Sima, the oceanic plate, okay, it has density of 3. Denser objects are much more compressed. Their per unit mass is more. So oceanic plate is always the heavier plate. It is always the heavier plate. So it totally nullified the Alfred Wegener's theory, who assumed that the Sial is floating over Sima. He said no, they both are adjoined. He accepted the mechanism of convection current theory, that the mechanism of hotspot, that how the plates are moving. Although the biggest criticism of convection current theory, he could not explain the random distribution of hotspots. Why the hotspots are randomly distributed, he could not explain. Okay, and even the plate tectonic theory could not explain this. So this he considered as a single plate. That is, a plate can be a combination of ocean and continent. It cannot be isolatedly ocean or isolatedly continental plate. It is a combination of both. I hope you are getting my point. Okay. So on the basis of this, he divided the whole world map into 1, 2, 3, 4, 5, 6, 7. Okay. 7 major plates and 22 minor plates. I'll share the PDF into my Telegram channel. My Telegram channel link and my Insta link is given into the, I would say, description box, channel's description. So what he did, Antarctica, you just see the plates, major plates. The first one here is Antarctica plate. This is Antarctic plate, South American plate. Second, North American plate. What is doing here? In the North American plate, see, this is the continent Sial part and this is the Sima part, Pacific Ocean Sima part. They both are joined with each other. Okay. Pacific plate, ocean, it is the largest and oceanic plate. African plate, fourth plate. Eurasian plate, fifth plate. Indo-Australian plate, sixth plate. Okay. So these are the prominent plates, major plates: Antarctica, North America, South America, Pacific, Indo-Australia, Africa, and the Eurasian plate. This is the Eurasian plate. Okay. So these are the 7 major and 22 minor plates. Cocoa plate, I'll show it into the map. Okay. You can see we have Coco Plate here. Coco Plate is between Central America and Pacific. Nazca Plate between South America and Pacific. Okay, like Filipino Plate, lot of plates are there. You just see the PDF. Okay, Arabian Plate, Caroline Plate, it's between Philippines and India. Okay, Fuji Plate, Australia. Asian Plate, Mediterranean Sea. Okay, Caribbean Plate, Central America. Juan de Fuca Plate, Pacific and North America. Okay, it's between Pacific and North America. It's a oceanic plate. And Iranian Plate. He considered plates to be the mixture of both ocean and continents. Some of the plates can be true continents, some of the plates can be true oceans. And now what did he said? He divided the whole world into certain plates, that is a combination of Sial and Sima. Now he said that all the plates are moving. Why they are moving? Because of the divergent currents. All the plates are moving and these plates interact with each other. The first type of interaction, the first type of interaction is convergent boundaries. When two plates are colliding with each other. Okay, when two plates are colliding with each other. Divergent plate boundaries, when two plates are moving away from each other. Transform edge boundaries, when two plates are rubbing each other, like this, rubbing each other. Collision, convergent, divergent, and rubbing. Okay, this is rubbing, lateral rubbing. Okay, so it leads to the formation of various type of landforms. And here our lecture of volcanism, earthquake, and mountain building starts. I'll deal these topics in a separate lecture, but I'll just give you a decent idea that what this is all about. Okay. First type is divergent plate boundaries. We saw in the case of thermal convection current theory and convection current theory, the plates are diverging. The plates are diverging and mid-oceanic ridges are formed. New crust is being formed here. Okay. So it leads to silent volcanism. Here what we see, ridges are formed. As you can see, the plates are diverging. Because of the convection current theory, the plates are diverging and the plates are breaking away. The best example is African Rift Valley. Block mountains are formed. Rift Valley, Ramp Valley are forms. I'll explain each and everything in the next lecture of formation of mountains. In this year UPSC, there were questions that what are volcanic mountains, what are block mountains. Okay, they gave it on the match the following. Okay, where you can see these type of plates. Vosges ranges, France. Black Forest ranges, Germany. In India, Satpura and Vindhyachal, they are block mountains. They are formed because of divergent plate boundaries. Okay, the structure is similar. The structure is very similar to like this. These are the blocks. Okay, these are the blocks. The part which subsides down is said to be graben, and the upper part is said to be horst. Okay, the mountains would be dealt in a separate lecture. It is a 1 to 1.5 uh, hours session. The next is convergence of the plates. Okay, what's happening here? Let's say this is a oceanic plate. High density, what we saw about Sima, it is high density, okay, and thin plate. And this plate is Sial plate, the continental plate. What would happen? What would happen? The Sima, being the heavier one, when it collides, it will subside down. Subside to where? In the mantle region. And in this region, when both the plates will collide, whole mountains would be formed. This zone would be called as zone of Benioff. Maximum earthquake is visible here. Now what happened when the plates subsides down? Okay, the oceanic crust is made up of basalt and gabbro. It is actually the rock structure. In high temperature, in very high temperature, they gets melted away. When they get melted, the olivine structure get melted. Okay, what would happen? When they get melted away, okay, like just imagine when you boil water. By boiling water, what you get? Okay, and the steam is formed. Okay, the steam is formed. The steam, it becomes lighter, it starts moving upward. It starts moving upward. And when it starts moving upward, okay, it becomes lighter. The same thing is happening here. The olivine rock, the bottom of the ocean, it gets melted away, it becomes lighter, and along with the magma, it starts rushing towards the surface. And in the continent, it strikes the continent and erupts in the form of destructive volcanoes. Okay, as you can see in this diagram, the lithosphere, the oceanic crust is going down. As you can see, it is getting melted in the asthenosphere mantle, and the convection currents are rising, and you can see volcanoes, the destructive volcanoes are formed, breaking the continental crust, breaking the seal. Okay, don't worry, the volcanoes would be dealt in very, very detail. All right. And the third part, it is the interaction of the plates. We call it as transform edge boundaries. When you can see the image, one plate is going down and one plate is going up. They both are rubbing against each other. So here, small mountains would be formed. Small mountains would be formed. For best example is San Andreas fault. Okay, it is the third case. Another case of convergence is there. Okay, it is said to be convergent plate boundaries or destructive plate boundaries. Why? Because oceanic plate is getting destroyed here. Let's say, if let's suppose the scenario is somewhat like this. Both continental crusts are colliding. The earlier case, what we saw, the collision of Sial and Sima. Now Sial, continental crust is made up of granite and andesite. When they both are colliding, both are equally dense, so no one is going to get down at the mantle. No, none of the plate is going to get destroyed. But on their collision, the fold mountains like Himalayas are being formed. How it is formed, why it is formed, we are going to deal this in a separate lecture of mountains, volcanoes, and different aspects. So people, this was about the session. I hope you liked the session. Okay, in the next session, what we are going to deal next, we are going to deal the volcanoes in detail, 1 to 1.5 hour session. Okay, earthquake, volcanoes, earthquake, and mountain building, types of mountain. 2 to 2.5. The basics are the same. Okay, so this was about the session. Thank you so much, people. Bye bye, take care, and Jai Hind.